Hi everyone, let me begin by thanking the organizers for giving me the opportunity of presenting my research on non-supersymmetric branes and discrete topological terms. Today I will be talking about a paper I published together with my collaborator Ivano Basile. What's the motivation behind this study? String theory provides us the best candidate for an unified theory of quantum gravity. And within this framework, supersymmetry has always been occupying a prominent place, both for the theoretical structure of the theory and for its phenomenological implications. But despite this, supersymmetry has not yet been discovered in high-energy physics experiments. So for this reason, and also for a purely theoretical interest, in my opinion, it is crucial to study the consistency and the structure of theories where supersymmetry is absent or broken at the screen scale. And this is exactly my goal for today's talk. Indeed, I'd like to give you some ideas about the study of some features of a particular non-supersymmetric theory. Indeed, there is a single heterotic theory without the tachyon, which is non-supersymmetric, and this is called SO16 times SO16 theory. In particular, I'd like to give you a proof of the existence of a discrete topological term in the space-time action of this theory, following the work of Yuji Tachikawa and Hao Zhang from a couple of years ago. I'd like to compute the value of the discrete topological term, and in light of the existence of the discrete topological term in this theory, I want to prove the consistency of a tentative spectrum for the NS5 brane. Indeed, a couple of years ago, Ivano, Arun, Matilde, and Miguel give us a proposal for the spectrum of such non-perturbative objects. This is my idea for today's talk. I'd like to start with some introduction about non-supersymmetric heterotic strings and anomalies, because I'd like everyone to be on the same page. And then I will delve into the proof of the existence of the discrete topological term, following the work of Yuji and Hao. And I will conclude with some ideas about the approach that me and Ivano employed in the paper. So in 10 dimensions, there are 5 supersymmetric string theories with a very rich net of dualities. But together with the supersymmetric landscape, we also have 3 non-supersymmetric 10-dimensional models which don't have the tachyon in their spectrum. And these are the Sugimoto model, the Sagnotti model, and the SO16 times SO16 heterotic model, which will be the theory of interest for today's talk. And as I said before, this theory is quite peculiar because it's the only 10-dimensional non-supersymmetric heterotic model which doesn't have the tachyon in its spectrum. Now, let me take a couple of minutes to discuss some features of the cousin supersymmetric theories of this model. Indeed, we have 2 supersymmetric heterotic theories, which are both endowed of a space-time gauge group, which is an E8 times E8 gauge group for the HE theory, and a spin 32 mod Z2 gauge structure for the HO theory. Both of these theories account for NS5 branes, which are non-perturbative 6-dimensional objects whose chiral spectrum has not yet been completely understood. In particular, these endow a rank K E-string theory in the case of the HE theory, and an SPK gauge theory for the HO NS5 branes. The latter was studied by Murad in the 97, who computed the anomaly polynomial and showed that there is anomaly cancellation via inflow in this theory, employing the S-duality with type 1. Last but not least, both of these theories have non-vanishing anomaly polynomial in the space-time, but both of them have a Green-Schwarz mechanism which cancel this anomaly in the space-time. Now, why am I talking about supersymmetric theories? The reason is the following. The chiral spectrum of the non-supersymmetric heterotic theory can be understood as a subtraction of the chiral spectra of the supersymmetric ones. And this is true also at the level of the anomaly polynomials. Namely, we can combine the chiral degrees of freedom of the 2 theories with a different sign of the chirality, and branching the representations of these 2 gauge groups into their common subgroup, SO16 times SO16, we recover the chiral spectrum of this theory. Now, the anomaly of a general d-dimensional theory is encoded in what we call anomaly polynomial, which is a d plus 2 form. And as a d plus 2 form can be decomposed in this way. So basically a purely d plus 2 piece and then a product factorized structure, like a 2 form times a d form, and so on and so forth. Now, if the anomaly polynomial is non-zero, either our theory is inconsistent, because there is a perturbative anomaly, or we are neglecting some anomaly cancellation mechanism. The first and most famous one is the Green-Schwarz mechanism, which is based on the existence of terms such this one, which may cancel the anomaly if the anomaly polynomial factorizes, so if this d plus 2 piece is 0, and if the gauge variation of the p-form field in this equation is non-trivial. And accounting for the non-trivial gauge variation for the p-form gauge field, it means that we have a non-trivial Bianchi identity for its field strength. And in the case of p equals to 2, this corresponds to having a string structure. Now, if the theory accounts also for lower dimensional defects, we must consider that these host chiral quantum field theories that may be anomalous on the worldvolume. And in computing the anomaly of the worldvolume theory, we must account also for the coupling term, because the coupling term between the defect and the bulk gauge field has a non-trivial gauge variation, which is ruled by the Green-Schwarz mechanism in the spacetime, and localizes on the worldvolume of the defect, contributing to the anomaly of the defect itself with what we call anomaly inflow. Now, if we want a fully consistent theory, we must require the exact matching between the worldvolume anomaly and the anomaly inflow. Everything I've been telling you until now is related to perturbative anomalies, which are anomalies of what we call small gauge transformations, namely transformations which are connected to the identity of the gauge group. Now, we can consider also transformation which lies in this connected component of the gauge group. And these are dubbed large gauge transformation, and their treatment is way more involved because they may give rise to what we call global anomalies, which are encoded in fundamental groups. Namely, the global anomaly of a d-dimensional theory is encoded in pi d of our gauge group. And here there is usually a misunderstanding. These global anomalies are not anomalies of a global symmetry. These are called Toft anomalies. We are discussing still gauge anomalies, but simply related to elements of the gauge group which lies in disconnected components with respect to the identity. Now, perturbative and global anomalies are recollected in a modern understanding in what we call Diefried anomalies, which are classified by a more involved mathematical structure, the Bordins group. A Bordins group is a set of manifolds with some properties, for example, to have a spin structure or a string structure or some gauge bundle, quotiented out by an equivalence relation, which is for two manifolds to be bordant. Namely, two manifolds are bordant, thus are identified in the same equivalence class of the Bordins group, if they can be seen as the boundary of an higher dimensional manifold. Now, Diefried anomalies are classified, of a d-dimensional theory, are classified with a d plus 1 dimensional Bordins group, which with all the decoration inherited by the theory. So spin structure, string structure, gauge bundles. Now, Tachikawa and Zhang showed that in the SO16 squared theory, there is a discrete topological term, which is a global counterpart of the Green-Schwarz mechanism. These terms are classified by Bordis group. Again, in this case, we must look at the d-dimensional Bordis group with a string structure because the heterotic non-supersymmetric theory has this feature, and this is equal to Z6. And in particular, in this talk, we will focus on the Z3 value discrete topological term of this theory. Now, in the following, I will show you how Yuji and Ao prove the existence of the discrete topological term. And this is a quite involved mathematical procedure, but the important thing is the take-home message that I will stress at the end of this discussion. So let's consider a 10-dimensional theory with a Green-Schwarz mechanism. We can integrate it by part. Now, the mathematical engineering of this method is based on a peculiar choice of the background for this theory. Namely, we can choose M10 to be a vibration of a three-sphere with a non-trivial H-flux over a 7-dimensional manifold. And we can further specify the 7-dimensional manifold to be a radial coordinate times a 6-dimensional submanifold. In this way, we can integrate over the fiber this Green-Schwarz term, and obtaining this result, we can interpret it as anomaly inflow on the world volume of the 6-dimensional defect, which corresponds to the NS5 brane. This is possible if we require the radius of the three-sphere to shrink to 0 while approaching the 0 of the radial coordinate. Now, besides the technicalities, this is a mathematical tool we have that shows us a correspondence between a space-time feature and a world volume information, namely between the Green-Schwarz term in the space-time and anomaly inflow onto the world volume of our defects. So there is this procedure that shows us this correspondence, and then we must ask, being on the world volume of our defect, an exact matching between anomaly inflow and the NS5 brane anomaly. Now, the NS5 anomaly can be a local anomaly, which is a perturbative contribution that is cancelled via perturbative anomaly inflow. That comes from the localization of the perturbative well-known Green-Schwarz term. But if we have a global anomaly, and indeed, in this theory, we have a global anomaly, this is a discrete phase in one dimension higher, and must be cancelled by a global counterpart of the anomaly inflow, which will correspond to a global counterpart going backward in this direction of the Green-Schwarz mechanism in the spacetime. And since we have a global anomaly on the NS5 branes of this theory, this is the way in which Eugenau showed the existence of a discrete topological term in the spacetime of this theory. And also, this strategy is quite powerful because if then you want to ask, what's the value of this discrete topological term? The answer, because of this exact matching, will be simply computing the global anomaly on the 6-dimensional theory of this NS5. And this is exactly what I will do now. Our aim is to compute the global anomaly of the NS5 world volume theory because it corresponds to the value of the discrete topological term in the space. An NS5 brane breaks the spacetime Lorentz symmetry from SO1,9 to SO1,5 times an SO4, which can be further decomposed as two copies of SU2. And one of them can be interpreted as R symmetry. Now, the claim of Eugenau is that the SU2 R symmetry bundle is enough to detect the discrete topological term in the spacetime. And thus we can set to 0, set to be trivial, all the other bundles we have. So the SU2L or the world volume and spacetime gauge bundles. So we are simply left with a 6-dimensional SU2 theory. And the global anomaly of such a theory is encoded by the pi6 of SU2, which is non-trivial. So it seems that there is a global anomaly. The point is that if we require the existence of fermion on the world volume, we must consider the spin Bordins group in 7 dimensions, which is trivial. But fermions introduce perturbative anomaly. So we need to cancel this perturbative anomaly. And we must require the existence of a three-form field with a non-trivial Bianchi identity to have a local 6-dimensional Green-Schwarz mechanism. And this is responsible, the requirement of having a 6-dimensional string structure is responsible for the reintroduction of a global anomaly on the NS5 world volume. So again, we have a 6-dimensional SU2 theory with a perturbative anomaly polynomial that is cancelled via 6-dimensional Green-Schwarz mechanism. Now, in principle, this six-dimensional anomaly polynomial is not known because we cannot access the world volume theory of the NS5. So Yuji now make this ansatz. Basically, the 8-dimensional anomaly polynomial on the world volume of the NS5 brane in the non-supersymmetric theory is the subtraction of the supersymmetric anomaly polynomial in the of the NS5 in the supersymmetric heterotic theories. In particular, as I said before, this one was computed by Murad in the 97 using S-duality to type 1, while this other piece can be computed using M-theory inflow. And once we have this perturbative anomaly polynomial, we require this 6-dimensional Green-Schwarz mechanism to cancel it. So we cancel perturbative anomaly. But the global one remains. And this is a discrete phase in 1 dimension higher and is formed by a contribution of the fermions encoded in the eta invariant and an extension of the 6-dimensional Green-Schwarz mechanism. So Yuji now computed this discrete phase, which corresponds to the discrete topological term, using standard methods, and they found that the global anomaly of this theory is equals to t, a parameter t, over 12. And in particular, they computed t to be 8. Now, 8 over 12 is 2/3, which corresponds to -1 in Z3. So they found a consistent Z3 value for the discrete topological term. Now, let me go to what we did together with Ivano in our paper. Our approach was a bit different. We acquired another perspective, starting directly from the chiral spectrum of the world volume of the NS5 in the non-supersymmetric heterotic theory. So we consider a general SU2 spectrum, which gives us the following anomaly. So we have a certain degeneracy of trivial representations, of fundamental representations of SU2, adjoint representations, and also we considered that in 6 dimension we have a notion of chirality for self-dual fields. Now we require 2 simple facts about this general SU2 spectrum. Namely that the anomaly polynomial has to factorize in order to be cancelled via 6-dimensional Green-Schwarz mechanism. And we require the matching with the proposal of Ivano, Arun, Matilda, and Miguel coming from this paper. Doing so, we find some constraints, namely that the full spectrum depends only on a single free parameter that we choose to be the number of adjoint representation of SU2. Now, the natural question is, what's the global anomaly of such a chiral spectrum? Or better, what's the discrete topological term that arises from this spectrum? Well, we computed the global anomaly, finding 124 plus 36 n3, which modulo 12 is simply equal to 4. So we found t equals to 4, and the global anomaly was given by 4 over 12. So basically we found 1/3, which is +1 in Z3, which is a consistent Z3 value, but there is a sign discrepancy with respect to the result of Yuji and Ao that I will discuss in the conclusions. Furthermore, we repeated this analysis turning on the gauge bundle of the spacetime in order to see whether the repackaging of representations with respect to SO16 times SO16 gave us some restrictions, some obstruction to the factorization, for example. But we found none, and also the suggestion that the number of adjoint representation of SU2 has to be 0. And honestly, this is reasonable to me because I have no physical interpretation of a adjoint representation of the SU2 bundle, which is coming from the transverse Lorentz symmetry. So let me go to the conclusions. I hope that I convinced you of the existence of a discrete topological term in the non-supersymmetric heterotic theory following the work of Yuji and Ao. And I computed its value, computing simply a global anomaly on the world volume of these defects. Then, taking into account a proposal for the chiral spectrum of the NS5 branes in this theory, I showed you that this gives a correct Z3 value topological term, but we observed a crucial difference with respect to the computation of UG now. Namely, there is a minus sign discrepancy. And this opens many interesting questions and research line that I'm tackling currently. So, namely, is there any issue in considering M-theory inflow as the NS5 anomaly in the HE theory? Or maybe there is some problem in considering only a perturbative spectrum on the NS5 brane in the non-supersymmetric heterotic theory. Maybe we are neglecting some non-perturbative contribution that may be quantified. And also, now that we are understanding a bit better the embedding of non-supersymmetric strings within M-theory framework, is there a way to perform the same NS5 anomaly computation directly in the non-supersymmetric theory? These are all research lines I'm currently following. And also the other possibility may be that none of us is wrong, but we simply discovered two different sectors, two different theta angles for the same SO16 times SO16 theory. And this possibility, in my opinion, is the most exciting because this means that we have new physics to be discovered and studied in the future. And with this, I'd like to thank you very much for your attention.